And recording. Hey, hello. Welcome back to another video. Welcome back to day 12, Hot Springs. I have everything opened up as I left it yesterday, and I don't remember much of... I do remember what the problem is about. In fact, I had been thinking about it on and off since yesterday, but I haven't come back to it. I wanted to come back to it at night, but well, I was a bit tired. To be honest, I really want to... Like, I'm very tempted to skip this and go do the rest of the days, day 13 and 14, because we are already on 14th of December. But also I'm a huge completionist. I really want to complete things. So I thought, well, let's scope this in time, give this a limited amount of time to try something, and if it doesn't work, well, it doesn't work. We have already gotten part 1 answered for this, but part 2 we had like an explosion of complexity, basically. So yeah, what I have been thinking, I have 1 or 2 ideas I would like to try out. First idea is trying regular expressions. So this problem, we have this kind of inputs, and I was thinking, well, the left part of this kind of looks like regular expressions because it has these wildcard characters. Let me put my phone in not disturb mode. Great. But actually, the right hand part of these inputs sort of work like regular expressions. So imagine, for example, well, any of these, but I mean, they're probably more interesting in the actual input. I can close this tab also. But if you have any of these list of numbers, it's quite easy to think about a regular expression that would match any possible input, should I say, like that would tell you if a pattern corresponds to these group numbers. So you would say like, okay, this means there's a group of 1 hash, but they can be any dots at the beginning. So you would say, okay, something, actually, let me sketch this out. Yeah, let's actually think about this example, which is the interesting one from the sample that has 10 different possibilities. Yeah, I want to use this as an example. So let's say this is the string, and the regular expression for 3, 2, 1, how would it be? My keyboard is full of cat hair. I'm trying this out in JavaScript because, well, I know a little bit about using regular expressions in JavaScript, but I have never used them in Rust, so maybe this is faster for trying this out. So first of all, we would say, okay, there can be any amount of dots or question marks, because like we want to accept things that can have question marks and want to say, okay, could this thing possibly match this pattern? We know that yes, because this is from the input, but for example, if it would have 1 extra hash here, it should say no. If instead of this hash it had a question mark here, it should say yes, because that could be a hash and it could match this 3. Let me bump the font size here. And it should have, and if it would have, I don't know, a hash here, it should say yes, because it could match the 2 or 1, and so on. So how would you say this? Okay, first it has to start with any amount of dots or question marks, so we can write this as this, I think, and any amount would be an asterisk. then it should count a group of 3 hashes. So maybe we could write, I'm writing it between square brackets because, this symbol shouldn't be anything on regexes, but okay. Should be 3 of these, but not only hashes, because we should also accept question marks. So a pattern of all question marks, it will match, which is right. And then we need the separator between each group, which would be again a combination of dots or question marks. But this time we cannot use the asterisk. The multiplicity of this should be 1 or many, and this has shorthand syntax, which is the plus operator, right? So this, let me grab up to here. I can also bump the size on here, I guess, to read it better on the video. And for my poor eyesight, this would be the group of 3 plus the separator after it, the separating dots after it. So let's copy this and do the same for the group of 2 that follows after, and then the group of 1. Here I could omit this, but I guess no harm done. And after the 1, there shouldn't come a separator between groups, but there can be, again, many dots. Okay? I think this should be the kind of regex that I want. And if we do regex test the string, it already tells me true. This is really nice of the dev tools of browsers. So we can, let me copy actually the string that we were using. So we know that this is true. If we remove this, it should still be true. But if we put another hash here, oh, it said true. I did something wrong. Why is this true? This shouldn't be true. If I put a dot here or a dot here, I think I screwed something up. I definitely did, but how much does this? Well, there is false, sure. At this point it's true. It could have a 2 here and a 1 there, okay. So if it has 2 hashes and 1 hash, this is still true. This shouldn't be true. If we have, I really screwed this up. I thought that this was going to work. Could the dot be matching? Actually, I don't know if the dot. No, I'm pretty sure that between square brackets, the dot should not match any character. So if we test for a dot, it's true. If we test for anything else, it's false. Okay. What am I missing in this regular expression? Could it be that I am missing the delimiters of, like, it has to start here and end here? Maybe that's the case because, yeah, otherwise it would be like matching anything inside, and the extra stuff that doesn't match. Let's try this. And if we test the string, actually I had it copied on the clipboard. Let's paste it here. If we put a hash here, okay, now it says false. I think maybe it was that. If we put question mark here, it still matches true, but if we say dot here, okay, it's false, because it cannot match the 3 group. And actually, for example, if we have a 1 hash is true, sure, 2, but if we put 3 here, it's false. Yeah, now it seems to be working as expected. Yes, look at that. That's really nice. That is really nice. I love it. And let's put it like this is still true because the last hash could be here, but if we put the dot here, it's false. Awesome. Okay, so we have generated manually generated with our brain a regular expression that can test any string of these three symbols and tell us if it can match this group of what was these things? Broken hot springs, sure. So that is my idea would be to try this out in our Rust program, because let's try to remember what we had here actually. We have this main recursive function of count possible arrangements. And what we were doing here is, okay, try to find the first unknown index, so the first question mark, and try out both possibilities of it being a dot or if it being a hash. And we were asking this is possible, but this we never implemented this function correctly, so we are saying, okay, it's always possible. But now we can probably implement this in terms of that approach of doing a regular expression pattern. But okay, let's describe what we had so far to also like remember in my head. We were telling if it is possible, and the idea of this function was to not be 100% correct. It might have some false positives of saying, okay, it is possible, but maybe it's not actually possible, but it shouldn't have false negatives. So it shouldn't say false when there are actually some arrangements that could be done. And so then we call this recursively, and we have another function, this one, row matches, that is actually doing our matching of a row, but now the row that shouldn't have unknown, let's say question marks. In this case, the row doesn't have that, and we can do also this match with a regular expression actually. And I think even we won't need this if we have a perfect regular expression that matches these things, which I think we can have, as we just saw. So that would be the idea of using regular expressions. But why do I think that this might help? Well, because we were thinking about this. The idea would be to cut the recursion and the unnecessary recursion when things are not possible to have. So for instance, in this case, if we try a hash here, that's already impossible. We should know that before evaluating all the possibilities of this of these question marks. And writing that logic, to me at least, feels a bit difficult to do. It's not impossible because we are going in order, searching for indices. So we could have like, okay, we are trying a hash here, and then we can advance up to the next question mark and say, okay, what is everything that I know? And it would be 4 hashes. And it's like, okay, do these 4 hashes match the pattern? And it would immediately say no, because this starts with a 3. So it's, you know, the most basic logic is not too bad. It's not too difficult, I think. But the regular expression, like my idea of using a regular expression is because, okay, that would still be, like the regular expression would encode all of these conditions much better, I think, than I would do with if statements. And it's a much precise match. Hopefully it is. And hopefully we can cut the recursion from here, and this should lower the runtime for part 2. Because in part 2 we're basically doing the same as part 1, but we are having like strings 5 times and groups 5 times the size. So that would be one idea. Let's take note of that actually and say, hey, plan, try regexes. Oh, I did Control S because I always do. Control S. Let's not save this. This is just another tab. Try regexes. But before trying regexes and regular expressions, let's also measure performance, or like where we are basically. Approximate performance. So I want to, again, I will keep doing Control S. So let's not annotate the plan here. Let's annotate it in the README. Let's put it there. Okay, that's our plan. Great. This is to have an idea of how long this is taking. Maybe we can do, well, measure how much part 1 is taking and seeing like if it's a significant amount of time, see how regexes cut this time, and so if it's worth it, to see if it is worth it or not. So that is one idea. The other idea, which I don't think I would do, or not like recording a video, because this would require a lot of like thinking in the abstract, and it's like actually understand the math behind this and like the combinatorial nature of this. So this is the interesting example here, and what we have is, well, the group of 3 to 1, which we just did a regex for, and for this starting pattern, we can basically know these 5, these 5 characters will be fixed. This must be a dot, and this must also be a dot for this to be a group of 3. So you can see that all of the possibilities match with that. Then it's like, okay, we are sort of seeing, we have this row of how many? 7 question marks, and we have to put 2 and 1 there. And putting 2 and 1 there basically means fixing 2 plus at least 1 separator and then the 1. So it's like fixing 4 characters. Because whenever you plot the 2, it's like, okay, you put the 2 here, the group of 2 here, it also fixes this next dot. So it's like then you have 4 places to play for the 1. And that's why you have 4 possibilities of this. And so the 10 is 4 plus 3 plus 2 plus 1. Okay, that also tells me that if we had, for example, another extra question mark here, what would happen? Well, we would have sort of the same pattern, but we would start with 3, the first place where you can put the 2. It's going to take 3 places, and then you would have 5 places to put the 1. So it would be 5 possibilities for that, and then you would shift the 2, and it's 4 possibilities for that. So it will be 5 plus this that we have here, which is 10. So it will be 15 possibilities. So I guess there is a pattern there, and I could make some sort of mathematical expression for this. And also then for part 5, these are the arrangements for part 1. This one is the interesting one with 10 arrangements. There's also this one, which is a simplified version, where you have a group of 6 and a group of 5 like fixed, and then a group of 1 that can move between these 4. So it is 4 arrangements. It's interesting to contrast that with this one, where there are also 4 question marks, but it's a group of 4, so that is only 1 arrangement. Okay, good. And then we have this one, which I think is also interesting, where you have 2 groups of 1 and a group of 3. The group of 3 has to be like fixed here, even though this is a question mark. It's like, okay, the group of 3 cannot these two cannot be anything else than the group of 3. And then each of these could be the group of 1 here or here, and the second group of 1 here or here. So there are 4 arrangements for this. And when we do the part 2, we have to unfold all of these patterns, unfold, and it's like you have 5 repetitions of this, joined by a question mark, right? And that increases the amount of possibilities by a lot. Let's actually look at this, like the answers for. Oh, this is a big, sort of big, not big. Well, we know that less than millions is fine for computers, but it's the answer for the sample on part 1 should be this. And the problem, I sound kind of defeated now, because our approach of doing like this regular expression matching, or what we want to try out, still haven't wrote it, would still require testing all the possibilities. Like, the only way in which we increase by 1 is this. Matches here is a boolean. It's nice. Like, we convert it to a 1 or a 0, yes. So we are always adding by 1 when counting the possibilities. We are never doing like, okay, here is 10, here's another 10, and having like multiplicity of things. So reaching these big numbers will require a lot of regular expression tests. And maybe these are rookie numbers compared to the actual input, because the actual input has rows of up to 20 question marks, and when we multiply that by 5, we're going to have 5 times 20, that's 100 question marks. Plus the 4 joiner question marks, so 104. So even if the regular expression cuts down a lot of possibilities, I don't see that working, to be honest. But I also want to, I want to try it out, because maybe I'm wrong. But yeah, these numbers are interesting. This is interesting, for example, 16. I think we can think about this, right? Because there are... Why is this 16, actually? The group of 4 can only fix here. So we had only 1 arrangement on the part 1. But imagine this thing repeated 5 times, and okay, it will be joined by a question mark. So the next group will be the same as this, plus a question mark in the beginning. So the group of 4 can be in 2 different places on the second repetition of this. Not in the first one, the one that on the leftmost side, but on the next one it can be in 2 places. And that will happen 4 times, because it's the 4 next, we need to multiply this by 5, and it's like 4 next repetitions. So it's 2 times 2 times 2, 2 times 2 times 2 times 2, 4 times. That is, well, to do the 4, that is 16. So this makes sense. And actually, isn't this another power of 2? Isn't this 2 to the, we said, to the 14? Oh yes, look at that. This is a power of 2. I should not know my powers of 2 better, I think, because this should have been obvious from the beginning. Okay. Why is this? So let's actually think about these examples, like in this mathematical combinatorial way. Can we run the examples actually? Because yeah, I think we have this thing killed for the actual inputs, but let's run it. Oh, inputs blah blah blah, sample txt. We didn't get to the answer, right? But let's see, possible arrangements. At least for the first one, it calculated 1. So yeah, this approach is so bad that we don't even get the answer for the exams. But I wanted to print this just to have the shape of things. So this is the first pattern, this one, repeated 5 times and joined with a question mark. So it's this pattern and then it joins with a question mark. And the groups is 1, 1, 3. So the 1 and 1 must be here and the 3 is also fixed. And it's only one arrangement. See, this is interesting because even though we are putting an extra question mark, it's like that question mark is sort of there to actually make it possible, because if we weren't joining with a question mark, then it would come 3 question marks and we couldn't be able to put a 1 and a 1 there, because without this question mark there wouldn't be a space to separate it with this group. So this question mark also is serving as a necessary space between the hashes. Basically that happens for all the, it's always the same and it repeats, and each of these it's just 1, 1, 3, 1, 1, 3 and so on, and these are the groups. So okay, this is interesting. One arrangement, easy. This is 2 to the power 14, and in the original, in part 1, it was 4 arrangements, because the groups of 1s could be here in 2 places and then here in 2 places. So 2 times 2 is 4. So why is now 2 to the 14? Well, let's think about it. We would have this same thing repeated again with a question mark here. The question mark here, okay, so 2, of course, 2 times 2 is 2 to the 2 to the second power, 2 squared. And if we do that 5 times, imagine if we join this thing, repeated the same thing, but instead of joining it with a question mark, we would join it with a dot. Then we will have 5 copies of this with a dot. The dot will do nothing. And it will be 4 possibilities each, or 2 to the 2. Multiplying those together 5 times is 2 to the, you had 4 possibilities for the first one, times 4 possibilities for the second one, that is 16 times 4, that is, I don't know, 16 times 4 is what? 256, is it? And so on. And the answer would be 2 to the 10, so 1024. But you also have the question marks in the middle, and those question marks can match with the first group of the second repetition. So that means that the first group can be there in that question mark, and then the second group can be on 4 places. So that increases the arrangements for the second repetition of groups by 4. It used to be 4, but now it's times 4 again, right? Is it times 4 or times 2? No, it's not times 4. It's 4 more arrangements, so it's times 2. So it's actually 2 to the 2 for the first repetition, because this wouldn't have the question mark separator. But then for the other 4 is 2 to the 3. So 3 times 4 is 12, plus 2 is 14, and that is the 2 to the 14 arrangements that we're seeing. I don't know if that was very clear to as an explanation, because I'm doing all of this in my head, in the air, and just speaking it out. But I think at least to me, it did make sense. This one is also super fixed, only one arrangement. And I guess that is only one arrangement because we are forced, the group of 6 is probably forced to last up to here. So let's see. I think if this is the group of 3, then you have a group of 1 that must be this, then a group of 3 that must be this, and then a group of 1. So, okay. And the revealed hashes are fixing things very much, and so this is nice. Then this is 16 arrangements. We have already thought about this. This is 2500. Why is that? Well, in the first repetition, we have 1 can go in 4 places. So we have 4. But then on the next one, we're going to have an extra question mark. So the 1 on the next group, like the 6 and the 5 are really fixed. But the 1 in the next group can be in 5 places. So we have 4 times 5 times 5 times 5 times 5. So it is 5 to the 4 times 4. And that is 5 to the 4 is 5 plus 5 times 5 is 25, times 5, 125, times 5, 625, I think. And times 4, yeah, 600 times 4 is 2400. And the other 25, yeah, is 2500. Okay, so there seems to be like a matter of repetition between these. So maybe the answer to part 2 can be like deduced from the answers for part 1, knowing how these things connect something. But I don't know. I feel like there must be some really nice mathematical way of thinking about this, and like combinatorial way, but I'm not really seeing it. And this huge number, what is, I don't know, that's not a power of 2, but what is this number? Let's copy it and actually let's throw it to the console. Here I was in bash because this was a previous analysis of things. Maybe I can do it in this console, which I'm already using fish. If we do a factor, not of this number, but of this bigger number, factor, the command gives you the prime factors of a number. So this is 2, 4 3s, and 5 5s. What the hell? 5 5s, interesting. Interesting, the 5 5s. So this is the pattern, the interesting one, the one that had 10 possibilities. 10 is 2 times 5, so those are the prime factors there. Can we actually think about what's happening? This is going to match another, like it's going to have another question mark and then up to here. But again, interestingly, the revealed 3 hashes forces the groups of 3 to be fixed on the same place for all of the repetitions, which makes all of these sample inputs quite simple. But I wonder if that is also something that's not simple, but like easy to think about, because we have some things on the groups that get fixed on each repetition of this thing. Whereas if it would be the case that, I don't know, the 3 from the second group could somehow be on some of the question marks from the first group, or overlapped in there, like I think that would make thinking about this much more difficult. But in the actual input, I don't know if that's the case, because we have some very long runs of question marks. In fact, I'm wondering if do we have a case? Oh, look at this one, for example. This is so many question marks. How many we have? This is also like so many question marks. There's some very long rows of question marks in the actual input. And what these mean, oh, look at this. Here we have just question marks. It's all question marks. So when we have 5 of these, it's gonna be hell. It's gonna be hell. I don't think that even the regular expressions will save us from this. Yeah, I don't think so. Because like we would have so many question marks and we would be like recurring. And it's always going to be possible until we cannot fix these 3 groups, but on the long string. And all the possibilities of that will be quite huge. But maybe there is another thing that we could do, which I haven't really thought anywhere deeply enough, but my last idea would be to try caching. So I don't know how to do caching on this, but usually in this kind of problems, it's like if you can think of a way to reuse previous calculations and cache them, that's usually huge. Okay. And I think like there are possibilities of doing hashing, like considering what we have seen so far, and so like what is fixed on the possibilities that we have, and how many groups that contains. If that is sort of like the hash key, and in this hash we would have like, okay, for this kind of the idea would be something like, let's think of an example here. Here we are, well, the group of 3 is not interesting because it's always the same. Then we have the group of 2. For example, if we have fixed, let's think of, these 3 possibilities and these 3 possibilities. What do they have in common? It's like, if we have seen, well, up to here, we have fixed the group of 2 here. Then we have already tried putting a hash in this position, and then that is the only arrangement for that. Okay, great. But then if we try a dot in this position, it's like, okay, if we try the group of 2 here and then 2 dots, then we have 3 possibilities, these 3 ones. Great. So we can say, okay, we have all of this string prefix fixed up to here, and these 2 groups consumed in this prefix. So we can put this into like a cache of results and say, okay, with this prefix and eating these 2 groups, actually only the prefix is needed because we can get the groups from there. Or something like that. Not the prefix, but the length of the prefix, just the length. Okay, this many characters we have seen. It's like, okay, and you have fixed the 3 and the 2 groups. There are 3 arrangements for that. And then when we are in this other possibility, it's like, okay, we also have seen the same amount of characters, fixed the same amount of characters in a different arrangements, because now the group of 2 is different, but we only care about how many characters we have fixed. And we also have fixed the same 2 groups in those characters. Then that should already be in the hash. And we can say, okay, that is 3 without computing anything. And this doesn't seem like much in this example, but this kind of caching can make a huge, huge difference on big examples, because you can just cut a huge amounts of computations. I don't know if that idea of caching, because that's something that I just had already seen, like looking at these things. But if that's the best way of caching this, or but it's one approach, and we could try this out. Okay, so that's the plan, and we have been like 40 minutes just speaking about, just talking, no coding. Oh, awesome. So, what should we do? And besides that, like this function can has some obvious things to like optimize if we wanted to optimize. Like we're making copies here of these rows and mutating them, but I think that we could do the same, like passing a mutable reference here and mutating this in place, and then putting things like putting back the question mark after you leave, and you would save some nice allocation savings. But that's not the main problem here. The main problem is that it's the sheer amount of unnecessary recursion calls and computations that we are doing. So we are not even getting the answer to the second sample problem. So let's first have some idea of where we are in terms of performance. So what I'm going to do is comment this printing out. I don't want warnings because they are so annoying. So let's comment everything out and just have this. Whoops. Okay. Great. No warnings, no warnings. Also no warnings here, please. And what I want to do is we can run this with a sample, right? No, but this will never end because we are also computing part 2. So we are unfolding the input. Yeah, okay, let's not print part 2. This will also generate warnings. Okay, that didn't seem very slow, but let's actually measure it. We are building, let's do cargo build and release. We have already done something like this. Time, blah, 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 but for day 12, hot springs, and feed it the inputs. Day 12, my face is on the way. Can we maybe put it to the side there? That wasn't great. Okay, day 12. Actually, with the actual input, which is larger, we can time this because we have the answer for part 1. Building release mode took some time, but this is interesting. The time it takes to run is not trivial. It's taking 350 milliseconds. That's nice. That's nice to know. And I wonder if we, well, that is for the actual input. Let's test with a sample. For the sample, it's nothing. Okay. If we try to do the unfolding for the sample, we know that this doesn't finish. But let's do, instead of an unfolding of 5, let's do an unfolding of 2. Okay. We're gonna run with a sample. And now the sample went from 1 millisecond to 50 milliseconds. That's a nice increase. And I wonder if the actual input can run with this already like folding of 2. Maybe it won't ever finish. Maybe I should add some printing. Let's get the printing back. The printing press back. Run. Oh, look at that. Most of them were pretty fast, but some are taking quite long. So it's very, very, very variable, the amount of time it takes for these things to run, which is to be expected. Some of them will have like stupid amount of combinations. So this is with an unfolding of 2. And it's taking too long. It's taking too long. I'm going to kill it. Okay, I don't want to use that as our sort of benchmark. Let's leave this like this. And you know what? Let's not unfold this, because the unfolding of 2 is already too long for the actual input. Doing something else less than 2, it doesn't make sense. Well, we can do 1, but that would result in the same thing. So let's leave the unfoldings here with 5s. Otherwise, I would probably confuse But let's do this, and let's just simply, you know what, do this twice, and let's just add them together. You don't like this because, are we consuming this here? Yes, we are consuming this, but I didn't mean to. So let's not pass this as a vector, let's pass this as a slice. Okay, I think there shouldn't be any harm in doing this. So we're just going to add this together. I want to have something that takes like a second or something like that. Yeah, this is good enough. Let's see if this is more or less stable. Yeah, okay, 800 milliseconds. So let's take note of this, like around 800 millis for 2 times part 1 on input txt. Yeah, this is very accurate in scientific measurements. Okay, that's great. This should be sort of a baseline to then do to try out the regular expression idea. Now I want to just commit what we have on part 1 and then like destroy this code and try regular expressions. We can even leave this. Yeah, did I put this in the answers txt? No. If we run now, I think this is with the actual input, right? Yeah, this was my answer. Day 12 is gonna be this. Sample out is, well, let's leave this. It's don't care. Don't care, don't care, don't care. Leave, oh, this thing that we introduced, yeah, okay, let's add everything except the plan on the README, and let's just commit this as work in progress part day 12. Yes. Okay. Okay, let's close this. So we have already measured sort of the baseline that we have. Now, doing the regex experiment. This is gonna be fun, and I'm saying that with a slightly sarcastic tone. Yeah. So I've never used regexes in Rust. How hard could it be, you know? There is a very nice regex crate, regex by Burnt Sushi, an amazing contributor, or yeah, contributor should not be the word, like a creator from Rust. Probably should check out the docs. And I know that there is also like a regex Lite. I have already seen this because, well, I follow Burnt Sushi on some discussion sites, and I know of the existence of this, which I think is kind of like just regex, but let's see, lightweight regex engine for searching strings, nearly identical to this, like the regex crate or regex searches in this crate have worst case O and n times n time, where m is proportional to the size of the regex and n is proportional to the size of the string. That's awesome. That's awesome. The principal difference between this and this is that the latter prioritizes smaller binary sizes and shorter Rust compile times over performance and functionality. Substantially slower. Yeah, you know what? Great idea of having like a lightweight compilation thing, but I think I want I will pay the price for longer compilation, but faster performance, please. So we have, okay, we have like a regex object that we can create. Here it is being created from a raw string. Okay. Then like it's extracting these groups. We don't need to do any group extraction or anything. We just want to like test things. So I guess that is there a test matches also. Oh, there are regex sets also. Interesting. Not necessary for what we are doing here. Oh, Unicode and things. This is also another thing that we are using not strings but slices of bytes, and I wonder if bytes. Oh, look at this. There seems to be some support for just byte arrays instead of Unicode strings. That's nice. So okay, let's start from sort of a simple thing. Let's start by doing cargo add regex. No, regex C, regex. Oh, that was fast. That was really fast. So, okay, great. Thanks, Cargo. I'm not used to package managers being that fast, to be honest. Okay, great. Let's do a simple case. Actually, do I still have the... Yeah. Let me steal this thing that we did. The regex will be this string, right? So I want to try this out, but on Rust. What if we do distance 1 inputs blah blah blah? So let's do it after this. Let regex be regex. Look at these, we have bytes regex. Let's first try the most common thing. I think using a raw string for this is probably not needed because we don't have any escapes or anything weird in there. And wrap. Okay. And regex, can you test things? Can you is match? Yes. Shortest match. Ooh, shortest match. I mean, captures each. I wonder, like, well, is match is probably what we want. So it's true if only. Okay, yes, I think this is what we want. But I was wondering also if, if we could use like the regex machine to sort of, like if we had these groups of hashes, like as capture groups maybe, if we could use the regex engine to say, hey, can you generate like all of the possibilities where these things could match? And it's like, that would be like the amount of arrangements, like delegating all the hard work to regex engine. I don't know if that actually makes sense in the idea of a regular expression, but anyway. I would expect this to match, right? So let's actually have something like let cases be, I want to try this. I want to try like, let's have 2, let's have 2 and 1. All of this should match, but let's let's also have one where it doesn't match because it is the beginning, one that doesn't match because of length, yeah, one that doesn't match because, well, there's a 2, there is a 1, but there is also another 1, okay, and then to like, hey, for case in cases, let's do is match that case, and println for case if it's a match. Okay, great. Let's run this. It doesn't matter if we run it with the input or not. Oh, now it has to compile. This is what regex lite was for. We're running this in release mode. No need for. Oh, we are timing things. No. Wait. I don't want to do any of this. I want to cargo run this with a sample, whatever, because, yeah, not in release mode. We can do a release build later. Okay. Look at that. It worked. Nice. So I can now put on my CV that I know Rust regexes. Let's spin up a release build so that the dependencies get built in release mode. Okay, great. So now we know a static case, but I want to run this thing as, sorry, I'm having trouble thinking. I want to generate these things, but also before that, let's go back to this and let's see if we can make these things. This is an array of string slices. Let's actually get this and say, hey, as bytes. And now each case is a slice of bytes, and this doesn't want to match. Yeah, you expected this. Nice. I like that the regex doesn't have like crazy types. But we know that if we don't use this and we import the regex from bytes regex, does this work? This is a bool. Oh, it seems yes, the isMatch call did work, but printing the case doesn't work because we need to convert this, and we could say like stir from I guess string from UTF-8. We can use the uncheck, but nah. Like we shouldn't need to check. And you don't like this? Yeah, sure. Come on. Yeah, this is a result. Oh man. Okay, finally happy. Can you run this, please? And it still worked. So we can match byte arrays. Awesome. Thanks, regex. Great for providing that. It's really, really useful to be able to match bytes slices instead of strings. So now, for the fun part, we have to generate these regexes. And I guess we can do this when we are parsing the records. For the records, we have the slice, the byte slice of the row, then the group numbers, and I guess we can put a third thing there, which would be like the regex that corresponds to that group numbers, something like that. Maybe we don't even need the group numbers themselves once we have the regex, but let's see. Yeah, we're gonna pass that. Other records. Okay. Possible arrangement sums. It receives this. Count possible arrangements. Yes. And when you count the possible arrangements, we are using the groups. Yes, for the row matches thing. Yes. Okay. So yeah, I'm thinking that instead of passing the groups, we can probably just pass the pattern, but let's just add it as a third parameter in there. So yeah, when we do this, we're gonna parse the record. Possible arrangements. Yeah, we can generate the patterns here, I guess, because this is our meat and potatoes function for part 1 and part 2. So let's say let regexes be records. Yeah, when we are counting, and we can even do it there. We have to avoid like generating the same regex many times, but this seems to be the right place to do it. So let's say groups regex generates groups regex for these groups, please. No, not regex. Regex. Please generate this. The order of this function is like kind of a mess, but okay, let's roll with this. This will return a regex. Sure. And it takes the groups. Okay, so let's copy what we have here, sort of as an inspiration. So the regex should have the start and end symbols or operators, I don't know how it's called, these things to say, okay, these are the things should be sandwiched between these things. Then this thing for the length of each group, and then a separator between groups. That sounds actually quite easy. Quite easy. yeah, let's just copy this. We're gonna have a sandwich. Let's not say regex, but regex string, whatever. We're gonna format. Let's leave these delimiter sandwiches. Eat everything else up to here. And in here, I want to put the groups, let's say pattern. Let's call this thing pattern. Full pattern. And then we're just going to return a regex new for this pattern. Actually, when we call new, how is this thing? Just re. Good. You know what? Let's follow that convention. Full regular expression, and this is going to be groups regular expression. And what is the groups regular expression going to be? Well, we're going to do here new of this, and here we want to panic. Like, this is an interesting thing, maybe. We generally are using like error propagation when, you know, we have an input that that is invalid or something like that. It's like, okay, we return a result, and here we could also like propagate any result because, well, this is giving you back a result. But actually, I want, you know, this thing shouldn't fail, that like the creation of the regex. If it fails, it's because there is a bug, and if there is a bug, we want to. I think it's better to crash and fix the bug. It's not like an error due to like an expected error that's from something that you can expect to happen if you have like an invalid input, for example. So here, yeah, I want to expect this and say generated regex should be valid. Okay. And the groups, okay, the groups regular expression is going to be groups. Gonna iterate them and map, and the mapping should be quite simple. I think we're gonna have a group, and we are gonna have a regular expression like this, just like this. But instead of the 3 there, we want to have the length of the group. The length of the group, yes. Sure, let's use a format again. In here, it's like we are creating a bunch of strings, but it's like, oh, okay. And how do we escape this? Oh, this is beautiful. So ugly. Length here, or no, let's just put in here. This is so ugly, man, but okay. We're gonna put in here the group length. Okay, this is the end of the map, and then we're gonna join all of this. Oh, the join comes from itertools. Okay. What a surprise. We're going to join with these separators. Okay. And you don't like these because... wait, what? Oh, this is already the group's length. Oh, okay, so groups, this is just a number, n, and we can just put n inside of here. I was confusing things. Okay. And this is full regular expression. And you don't like this because this is a string. Yes, sure. Let's pass a slice. Great. And I want to print line debug. So regex for groups is the full array. Okay, so now we should be generating groups. Yes. Let's do it for the sample. And look at this beauty. 113 is one separator, one and separator, and 3, and the last thingy. So this seems to work, and this for the generation of regexes. We didn't hit this expectation failure, so that is fine for the regex engine. Awesome. So now when we are counting possible arrangements, we are also going to pass the regex itself. So here we're going to take the groups regular expression, which is a regex, which is a reference to a regex. We're going to pass it around groups array. Sure thing. So far so good, but now the is possible is what we need to check. And this is where it should get interesting. So instead of asking is possible, we can just ask the group's regular expression if it is a match. If it is a match with this possibility or with this possibility, then it is possible, and we can do the recursive check. So groups a regular expression. Is it a match? This new row? Is this new row a match? And you don't like this because borrowing. What do you expect? Oh, this is a vec. Of course. We are allocating. I forgot that we were doing an allocation here. Fine. Let's put this here. We still have these row matches, which is not necessary, but this now should be cutting our recursion. So let's see if this works. For the sample, well, it printed the same result, that's for sure. We can get rid of this printing. We know now that, well, the generation of the regex actually was quite simple. That's good to know. That's always good when things are simpler than I thought they would be. So we can run this now. We can run with the actual input, I guess. It prints some warning. It actually looks like it took some time to run. Maybe compiling all the regexes does take some time, but if that time gets like reduced, like if it saves time in running, then it should be fine, but we should time this thing. So let's build in release mode. and run the thing with the actual inputs. And look at that, 96 milliseconds. That is an improvement from the 300 and something. Now, where did we? Well, in the README we annotated this, which was running the thing twice. It's still also printing the same result. So if we run this now with, well, it's not a huge improvement actually. It's still in the same order of magnitude, 800 milliseconds. Like it's 4 times faster, but not like 100 times faster. So it's not a huge improvement. And so I'm not expecting this to work for part 2, to be honest. So on part 2, we are unfolding the inputs. And then we have the unfolded records, which is just the same as this, fine. We can avoid these declarations here, I think. Oh, no, not really. Oopsies, sorry. Yeah, this is ugly to do like the parsing again, because we shouldn't be doing this, but okay, let's not worry about that. The unfolded records are this. Can this thing run for the... Sorry, I had to do this because of my face. Can this thing run for the sample? Built on, built in release mode and run for the sample. It actually finished running for the sample. We are not printing the answer 2, but let's print it, actually. This is exciting. Were we unfolding in 5? Yes, we are unfolding in 5. Look at that. And do we get the actual? Yes, this is the answer for the actual for the sample. That's awesome. I want to run for the input. I'm thinking that it won't finish in time. Let's run it. I don't think it will finish in time. It is running, and we don't see. I think I want to have this printing of when processing things. So let's do that. Let's comment this, and this is count possible arrangements. It should also receive these. Okay, did it run? No, it didn't finish yet. So let's run it again. So now it's running. This is a pattern for part 1, and this is the first pattern for part 2, 32 arrangements, 768, 7,000 and something. And now it's taking its sweet time, but it ran and it generated, oh, that was a big number, 7 million arrangements. Because look at the amount of question marks that are here. But the brute forcing with the regex is doing its work. It's doing a lot of work. This is promising. This is like, I could leave this running and maybe get an answer at some point. I'm actually a bit worried. Look at that, it also ran because I'm using 32-bit numbers, and I'm worried about possible overflows, because we are running release mode, and if we have an overflow, we won't know that because we are not doing like checked math, sadly. And that's kind of stupid. So I'm going to actually kill this, change the 32 bits numbers for 64, just to make sure that's to use big numbers. So yeah, let's change this, everything, I think. Count possible arrangements, sure, and sure. Okay, all of this, let's change with U64. Should still compile fine. We do have an error, I think. Oh yeah, the parse numbers thingy. Because this thing is hard-coded. We shouldn't hard-code here, but we are only using it for this problem, so no worries. This is possible. We can get rid of this. We are not using it. And actually, the row matches. Yeah, this is another stupid thing. We shouldn't do row matches like these. Yeah, we can just, you know, I think that this is not necessary. If we run with the sample now, well, it has to compile. Compiling is always boring. The sample took 800 milliseconds. Okay, but it's doing part 2, so it's doing its work. Yeah, 800 milliseconds, but we are finding, like, brute forcing 500,000 matches, and this is like 500,000 or much more than 500,000 regular expression tests. So thanks again, Burnt Sushi, for having done such a nice work with the regex trait. So I think here this should already be valid, because we are asking if it is a match when we are doing the recursive call, and this regular expression should be matching things perfectly. So let's actually run the sample and see if we still get the same. Yes, we still get the same answer, and it didn't really decrease the runtime, but we are doing, yeah, we are doing less checks, so this actually is not needed. I won't delete it because I think some of this logic might be useful later on for doing like caching and things like that. But okay, now let's run this with the inputs and with the 64-bit numbers. It's gonna take a while, but should be fine. Actually, before I killed it again, sorry for for being so undecisive, but I want to run part 1 again and see. Yes, this is the answer that we want, right? Yeah. Okay. Just to make sure that removing the check in here was fine to do. So now we are not using these groups for any sort of check. We are passing it around in the recursive calls, but it doesn't get used anywhere. So let's run this. This is doing a bunch of brute forcing for regular expressions, but maybe it will work. Maybe it will. I don't know. Maybe another good idea would be to to print the number of the line that we are matching against, right? That we are computing. So here, I guess, campus arrangement, blah blah. What if we enumerate this thing? So we have this and this. I mean, printing all of these groups and everything is like a bit noisy. Yeah, let's actually do the zip trick and have one base indexing, so it corresponds to line numbers. Yeah, and yeah, just have this, you know. What's your problem now? Oh, the zip. Okay. Yeah. I comes here. Great. Just to have an idea of where we are. And you know, these are 1,000 inputs. So input for day 12, they are 1,000 lines, and we are computing the line 4. So we know that it takes a while. We are now at line 8, and the number of combinations is quite erratic, but look at that, there's a power of 2 here. So yeah, it's clear the case that the most perfect solution would be to understand like the maths, like the combinatorial maths of these things, and like do multiplications of things and you know, just get to a number instead of like brute forcing all of the possibilities. But I mean, this could finish at some point. Look at that, we are already at 16. It's not fast by any means, but maybe if I leave it running for, I don't know, some minutes, an hour or something, I will get an answer. And you know, that would at least subdue my completionist brain to have at least, you know, part 2 answer, although I don't have a good algorithm for that. It's like, well, at least I got the answer. I am quite sad though that, you know, to be looking at this going so slow. But the regex experiment was a definite success. We did we did an impressive like optimization. Like this runs much faster than our previous approach, so that is nice. It's a very nice way of matching these inputs. I'm tempted to try the some stupid optimizations. Like the caching thing is the most important optimization that we could try. But it's almost an hour and a half of video already. Let's do a very stupid thing. I will kill this again because it's taking way too long. One thing that we could try, a very simple optimization, is not allocating here for this new row thingy, but instead receiving this row as a mutable reference and then mutating that. So we have the unknown index. We are gonna do, instead of new row, by new thingy, just use the row. We're gonna pass it as it is, and then we are going to put back the unknown index, put back the question mark here. Okay. And can we actually do this? Because now this thing, this is gonna be ugly. But counting the possible arrangements, it's like, okay, maybe we can cheese it here. We are passing the recursion like this. Sure, let's see if we are allowed to, if we have a mutable reference like this, can we have a mutable iterator for this? Okay, yeah, now we can pass the row as mutable, that's great. And we can pass this as mutable here too. We introduce our good old friends mutability everywhere. Kind of ugly, I know. But if we run this with, sorry, let's run this with the sample. It didn't affect, yeah. It didn't affect the runtime at all. So those allocations are not what the problem is. Okay, we can dial back the mutability on these things, right? Yeah, we don't need to do this. We don't need to do that. But maybe here we can receive this as a mutable reference, just that instead of passing the record as mutable, we can say something like, hey, let's row be the row to owned or to, yeah, to owned returns. Doesn't this return a vector? Owned data from borrowed data, usually by cloning. Yeah, that is. Oh, but this is a double reference. Beautiful, beautiful. Because this is a slice. We are mapping. Why is this a double reference? You know, that doesn't make that much sense to me. But well, let's not think about it too much. Let's do a to back, and here pass this thing as a mutable reference like this. So we can do the mutability thing in here, get back, run for the sample, and actually now it seems like it ran a bit faster. I don't really understand why that is, but it is printing still the same numbers, so that is fine. That is good for me. Sorry, I'm having stupid trouble. Is this always on top? Yes. Okay, I stopped seeing my face in the corner. Like, my face in the corner is kind of annoying for the built-in console here when I'm running long comments. Yeah, like I don't like that. If we make this a bit smaller, but not that much smaller, we can like make it. Yeah, we can make it something like this up to here, and running with the input, because otherwise I cannot read the thing. That optimization, of course, is not really that impressive at all. But you see, now I stopped seeing my face. Oh, shit. Oh, no, I don't want to see my face. Well, I lost my face. Damn it. Well, I hope that you can still see it, but yeah, this thing here, we don't need to pass the row as a reference, because it's a mutable thing for the same thing. yeah, that micro optimization, I don't think it will do any difference, but it makes more sense in my head instead of like making a unnecessary copy inside of here. I think that's sort of what I wanted to try, at least in this session. We got the thing running much faster than, like, at least now it may at some point finish running the part 2 for the actual input, and maybe it will be the correct answer. But what I would really like to try out is doing some sort of caching of these results, and so that would allow us to not be just adding 1 each time, and instead like reuse previous computations, and that should make things much better, I think. But it's not clear to me how we're going to do that. By the way, this yeah, this is not going to end anytime soon. I'm going to kill it once again. The isMatch check here, I think we could do something like do it at the beginning and say, hey, if it's not a match, return 0. And yeah, if it's not a match, return 0. And then here, not conditionally call this, like always do the recursion call, and the recursive call will immediately terminate if it's not a match. So it's sort of the same thing, but in another order. If we run this with a sample, now I can see the line because I cannot no longer see my face. But if we run it with a sample, we still get the same answer in the same amount of times. But I don't know, maybe this is easier to read as a recursive call. I'm going to leave the actual input running again. We can add this change. Yeah, we can commit this and say again, work in progress. Try out regex solution for day 12. So we have a thing that is working. That's great. It's taking its sweet time, but you know what? I think I'm going to end this video now and leave this thing running. I don't know, eat something and come back to it and see if we got any answer. If we got an answer, that would be awesome. But what I want to try is like the last thing that I want to try for this day is to try to see if we can do some caching of these results, which doesn't seem trivial to me, but also it doesn't sound that complicated. So yeah, that's going to be the next idea, and I am a bit toasted right now to try it now. So yeah, I will end the video. If you have watched this far, thank you very much for doing so, and see you in a bit, I guess. Bye bye.